That could be completely wrong. You don't have to. It just makes it easier to visualize it. I did. Because it's easier, because you cross stuff off. And then you see, okay, I'm only left with. You can just look at it like that. It's pretty easy. Yeah. I don't know. I don't think so. Yeah, it better not be. Yeah, it's going to get smaller. A lot of people are graduating.
Does that look right to you? H2 canceling with H2 over there. 1/2 O2 canceling with O2 over there. So we've got H2O becoming 2 H's and an O. The total enthalpy change is the sum of the enthalpy changes for the different processes. We had to multiply that guy by a factor of 2 to suit our purposes. 2 H's, so we got that factor of 2 in here. Sum those together, we got 927 kilojoules per mole of waters in the gas phase that are split apart.
Is the delta H for the 1/2 O2 to O, is it 249 or is it 249.2?
249.2.
Oh, okay.
Yeah, 249.2. So multiply that guy by a factor of 2, throw them all in there, sum the enthalpy changes, we got 927 kilojoules per mole, and that's for taking one water and breaking off both of its hydrogens. If you want to get the average bond enthalpy for that oxygen-hydrogen bond, you simply divide that by 2, and you get whatever 927 divided by 2 is 463.5. And again, the majority of that enthalpy change is associated with just that electric, the forces that the force that you got to apply to separate those charges from one another, right? There's the whatever atmospheric PV work had to be done as well. So,
why did you divide by 12?
because the question wasn't what is the total enthalpy change for this reaction. The question was, what is the average bond enthalpy for an oxygen-hydrogen bond in a gas phase water molecule, right? And so to calculate that, we figure out what the enthalpy change is for splitting apart an entire water molecule, and then assign half of that value to each individual bond. If you look at your book's going to tell you that the actual steps taken to do this aren't equal in energy, but we assign an average energy.
Oh, okay.
If you take one hydrogen and pull it off of an oxygen, and then subsequently you go in and you pull that other hydrogen off, you're going to find that the energies associated with those two are not exactly equal, but for the purposes of assigning average bond enthalpies, we kind of average those energies. Read your text, it should. Go ahead.
Shouldn't we get the same thing if you flip the two first equation instead of the last one or the third one? So instead of flipping the third one, you flip the two first.
Flip the two first ones.
Then you're getting a negative reaction. Then you're
As
getting
you're gonna get
the opposite reaction.
it. So we
Don't
can't do
ask
that.
me to do any math on the spot. I only do math that I've rehearsed thoroughly before I ever show up in lecture.
So that's because I did it, but I got the negative of that, so so we can't do that. So it was wrong.
Did you get the same answer?
But I got a
This is-
negative of that answer.
Just flip it over again.
Sure.
Yeah. She basically has the first reaction, the bond reaction backwards. At the end of the day, that's what you're doing. That H2O gas to 2H2 to O, when you calculated it, you had it flipped to O plus 2H gives you the H2O, and you have to turn it back the other way.
Oh, okay.
Because you have to get that top equation. That's what you're trying to figure out, and you figured it out, the reverse reaction.
Oh, okay.
That's why you're getting the negative.
Okay. Thank you.
Yeah, what he
Something like that.
Okay, so let's look at one more thing. So we said that we can take these reactions that proceed very quickly to completion, and we can measure the enthalpy changes for those reactions, and then we can sum those reactions and end up formulating all of these standard enthalpies of formations from the elemental precursors. We told you that can be done, and now we're just going to look at an example of that actually being done. We're going to look at a technique called bomb calorimetry. And bomb calorimetry is a process that you can use when you have a system that includes some gas phase precursor. The reason for that is that if you wanted to try to run a reaction that didn't contain a gas phase precursor, sorry, I have to say what I was just about to say. Bomb calorimetry is used when you have a gas phase precursor. You essentially put the reaction together into a container that doesn't allow any volume change. So if we run a reaction in a container that doesn't allow any volume change, and we measure the heat associated with that reaction, it's a constant volume process, what energy are we measuring? Or what state function are we measuring the change in? You guys remember the constant volume process? We said that delta something was equal to CV dt. It's the internal energy. So we have a constant volume process, and we have no pressure volume work being done. We measure the energy associated with that process. We're measuring the change in the internal energy of the system. If we were to take a reaction that had gas-based products and measure or run that under constant pressure conditions, that PV work would be hard to determine. So we actually end up going out about determining the enthalpy change in a roundabout sort of way by first measuring the change in the internal energy and then kind of augmenting whatever quantity we come up with to account for PV work. So real quick, here's our bomb calorimeter. We've got some reaction mixture, some reactants sitting in a chamber. That chamber is made of a diathermal material, which means that it transfers heat very easily. And outside of that, we have a bath of water that we know the mass of, and we know the specific heat of water. And so what happens is this reaction proceeds, and we're pumping, if this is a combustion reaction, we said the combustion reactions were very useful. We pump a bunch of oxygen down in here, and we run the combustion reaction, and some amount of heat is released. And the heat that is released gets dumped into several places. It gets dumped into the calorimeter. Because the calorimeter is in thermal contact with the water bath around it, it gets dumped into the water bath. It also, energy of some sort, gets dumped into kinetic energy of whatever the gas phase reactants are after the reaction proceeds, and the liquid phase reactants. So what we do is we run that reaction and we measure how much energy was dumped into each of these species, the water bath, the calorimeter, and we grab the magnitude of that energy and we set it equal to delta U. In order to do that, we need to know the heat capacity of the water bath, the mass of the water bath, the change in the temperature of the water bath. We need to know the heat capacity of the calorimeter and the temperature change of the calorimeter. That means that we'd have to run a reaction on this calorimeter where we dump a known amount of energy into it and measure its temperature change so that we can figure out how much energy is requisite to change its temperature by a certain amount. So let's give a hypothetical situation. Let's say that we have 0.857 grams of benzene, and we combust this guy into a calorimeter that has a water bath around it, and that water is 1.812 times 10 to the third grams of H2O. There's a calorimeter, and we've measured the calorimeter by dumping a known amount of energy into it and monitoring its change in temperature. And the calorimeter has a heat capacity measured heat capacity of 7.59 times 10 to the third joules per degree Celsius. Degree Celsius is the same thing as degree Kelvin, same size. And incidentally, water's heat capacity is equal to 75.3 joules per mole Kelvin. We throw this benzene in, combust it to completion, and we see that there's a delta T of this entire thing that is equal to 2.3 degrees Celsius. Right? Our job is to figure out how much energy was dumped into or was released by this combustion of the benzene. So we're going to say that our delta U, combustion, is equal to the energy absorbed by the calorimeter in water divided by the number of moles of benzene combusted. Right? And to calculate this, we've got to figure out how many moles of water we have. So 1.812 times 10 to the third grams of H2O. Divide that by the molar mass of H2O, 18.02 grams per mole. Gives us the moles of H2O. Multiply that by the specific heat, 75.3 joules per mole Kelvin. Multiply that by our delta T. The delta T was 2.3 Celsius, but that's the same thing as 2.3 Kelvin. And so this term represents the amount of energy that was absorbed by the water bath. Now we've got to figure out how much energy was absorbed by the calorimeter. We've got 7.59 times 10 to the third joules per degree Celsius. That's the heat capacity of the calorimeter. The calorimeter changes temperature by the same amount, 2.36 degrees Celsius. And so those two terms represent the total amount of energy that was absorbed by the water bath and the calorimeter in this process. Divide that by the number of moles of benzene, so 0.857 grams of benzene, 78.12 grams per mole, and we get some figure, and that is that our delta U, we're going to assign this a negative value because it was heat that was released by the benzene, is equal to negative 3.26 times 10 to the 6 joules per mole, right? So we just measured the heat released in a constant volume process, and we found that benzene, the combustion of benzene, is releasing negative 3.26 times 10 to the 6 joules per mole. How do we go from there to our delta H? What's the relationship between delta U and delta H?
It's like delta H equals delta U plus.
Delta U is equal to Q plus W? Q is
Delta
equal to
U is
delta
equal to
H.
Q plus W, but what do we do when we wanted to derive, when we wanted to come up with that enthalpy state function? How did we do it? What did we took the state function that we already had and we augmented it by a term that allowed us to account for pressure volume work that was done in a constant pressure process, right? What was that term that we added to it? We added the PV term to it, right? Because that PV term adjusted for whatever energy was spent in a change in the pressure or volume of the system. Constant pressure process, the pressure is constant, the volume changes, but there's a work associated with expanding or contracting against an external pressure. And so that PV term was the term that we added to the internal energy to account for energy changes associated with pressure volume work, right? Against contraction. And so, if we know our delta U, all we have to do is add to that a term that accounts for delta PV, and that'll give us our delta H. So delta H is equal to delta U plus delta PV. And to account for this delta PV term, what we do is we assume ideal behavior, right? For processes where we think that that's a safe assumption to make. Go back to the ideal gas law, and PV is equal to nRT. Theoretically then, delta PV is equal to delta nRT. If we assume the temperature doesn't fluctuate very much in the process, which isn't always the greatest assumption, but for these it's not a horrible assumption, we can say that delta PV is equal to the change in delta N, and right now we're referring to the number of molecules in the gas phase, times RT. You're going to see this coming up a lot in your homework problems. Your homework problems will tell you what a delta U was, and they'll say turn that into a delta H, or they'll tell you what a delta H was, and they'll say turn that into a delta U. And you're supposed to know that the difference between delta H and delta U is this PV term. So depending on whether you're going from delta U to delta H or delta H from delta U, you'll either be adding or subtracting this term, but that delta PV term is, if we're assuming ideal behavior, equal to delta nRT, right? So this guy, we calculated our delta U. We said that our delta U was negative 3.26 times 10 to the 6 joules per mole. And our delta PV, if we look at this combustion reaction of benzene, what time is it?
1052.
1052. Take my word for it, I'm not going to put the equation up, but basically, when we combust benzene with oxygen, our delta N of gas phase products, we end up with 3 less moles in the gas phase than we started with, and so that delta PV term ends up being negative 3 times 8.314 joules per mole Kelvin times 298 Kelvin, and the total delta H ends up being negative 3920 times 10 to the third joules per mole. Right? So we can figure out our delta H for that reaction by using the Baum calorimeter, running the reaction, and adjusting for, determining what delta U is, and then adjusting delta U to turn it into a delta H. All right. Good luck over the weekend. Check for videos. I'm going to put some stuff